ladies and gentlemen, class recording has begun. So, please refrain from any stupid comments. Questions are okay, stupid comments not. Okay? I am going to start us off today at this website. So this website is called the PAGT website. It's got interactive simulations. This is through the University of Colorado. They have a bunch of computer simulations that are out there to, real things out there in the real world. So today, I am going to play with Sims. Paper towel over. I'm going to play with Sims, and then I'm going to go into the physics ones. And underneath physics, there's one that is the Pendulum Lab. I am going to run that Pendulum Lab now. So, there's the Pendulum Lab. Okay? I'm going to start off by taking the bob of this pendulum and pulling it up to 45 degrees off of where it came from. And then I am going to let it go. And it's going to go like this. Okay? Great. Good there. Okay. But for our discussion, to make it a little bit more relevant, I am going to come down here where it says show energy of, and I'm going to click number 1. And then that's going to happen. Okay? I'm actually going to stop it here for a second. I'm going to reset it. And then I'm going to pull it here. Okay? And then I'm going to let it go. Like this. Okay? Alright. So over here on the side, there are 3 bar graphs that keep changing rapidly. If you can't see them, those 3 bar graphs are labeled kinetic energy on the left, potential energy in the middle, then there's one that's not being used right now, and then the one on the far right is labeled total. Let's zoom in here. There we go. Okay? First question. Is mechanical energy being conserved as this pendulum swings back and forth, back and forth, back and forth? Okay? A lot of you shaking your head, yes. Why do we know that potential or that mechanical energy is being conserved as this pendulum swings back and forth? Jillian, go ahead.
The total amount of energy doesn't change.
Okay, total amount of energy doesn't change. That's true. What's another way that we can tell from the mechanical energy standpoint? We know that because of what this graph is telling us. Okay? Trey, what is this graph? How do we know that from what this graph is telling us?
The pendulum keeps going to the same height.
Okay, potential keeps going to the same height, right? And that when potential goes down, what also happens? Kinetic goes up. And that kinetic goes down, potential goes up, kinetic goes down, etc., etc., etc. But to get to the conservation of idea, right? Trey, like you said, how high does the potential energy keep going each time?
Well, I said the pendulum.
Oh, sorry, the pendulum, sorry. Okay? So the pendulum keeps going to the same height each time. Meaning that if the pendulum keeps going to the same height, I'm going to try and stop it. Yep, didn't quite get it there. Let's go there, okay? At the end of its motion, right? What do we see about the amount of kinetic energy at the end of its motion? Christine? There is none, because what does the pendulum do at the very, very end of its motion? Stops. Just for an instant, but it stops. Okay? If that's the case, there's no kinetic energy. That means that all of the mechanical energy is in the form of what? Potential. Okay? As it goes down from here, right? Okay? Oh, it doesn't show me because it's paused. Right? But as it goes here, when it's close to the middle, what do we see about the amount of kinetic energy? Really high, right? And the potential energy has come back down. If we go all the way back over to the other side, okay? If we go back all the way over to the other side, right? Potential energy gets big again, no kinetic energy, right? But it always goes to the same height because the potential energy has to be the same. Good there? Okay? if we go back to, I don't have it open because the last class didn't do it. There it is. That's not what I wanted. Glad this is being recorded. There we go. Okay. On Monday, we talked about this lady falling out of the building, right? Okay? And we talked about that the same thing happens, that when she's up at the top, right, she starts off with potential energy. As she falls, that potential energy decreases, but the kinetic energy increases. Okay? On your outline, there is, what do you need, Andrew?
Nothing.
Oh, get that. On your outline, there is, I shouldn't do that one, I should do this one. There is this graph that is labeled Conservation of Mechanical Energy in Falling Objects. So, let's talk about the mechanical energy of that lady as she falls. What kind of energy did she start with? Potential gravitational, right? So I am going to use yellow to represent her potential gravitational energy. And it says that she starts here at 10,000, right? What about her kinetic energy, though?
It's at 0.
It's at 0, right? So I'm going to use red for kinetic energy. I'm going to start it down here at 0. Okay? Now, what do we say happens to her kinetic energy as she falls? It goes up. But if we examine that formula for kinetic energy, right? Ke equals 1/2 mv squared, right? Those of us that have taken algebra before, if you're in algebra, you might not know this, but if we've taken algebra before, right? If we have a squared value, right? What does the graph of a squared value look like? What does an x squared graph look like? It's a parabola, right? So this kinetic energy is going to go up, but is it just going to go straight up in a line like this? No, because of the squared idea, right? It's going to start going up a little bit like this, but then it's going to raise like that, right? Yeah. What did we say has to happen correspondingly to the potential energy? It has to. Good. It has to decrease, right? But is it just going to go straight down from here to there?
No.
No, right? These two graphs are going to have to be what of each other?
Congruent.
Not exactly.
Like it's both parabolas.
They're going to be both parabolas, right? But this yellow one's going to be which way?
Down.
Downward, right? The word I was thinking was that these two graphs have to be mirror images of one another, right? Because as one's going up, the other one's going down. Got it? Okay. I'm going to add a third line onto this graph, and it's going to look like this. That's supposed to be straight, and it's supposed to be, okay. It's a horizontal line that goes right along here at 10,000, right? What is that horizontal line at 10,000 representing?
Thermal.
No.
Oh, mechanical.
It's representing mechanical energy, right? So the red line is representing our kinetic energy. The yellow line is representing, is representing PEG, right? Gravitational potential energy. And then our orange line representing the total amount of mechanical energy. Does that make sense for this lady as she falls down to the ground?
Yes.
We okay with that? Kinetic energy goes up, potential energy goes down, mechanical energy stays the same. The shape, right, because of the way that this formula is, I should probably bring kinetic energy down here like this, with the other stuff, okay? But because of the formula, it's not quite straight lines. Good there, okay? I'm going to show you another graph. This graph looks like this. You don't have this graph on your outline. I just have it here. Okay? Can I move this over here? Thank you. All right. So, like the question says, is mechanical energy conserved in this graph? Discuss amongst yourselves. Is mechanical energy conserved in this graph? Go.
No, because that line isn't.
Yes.
Hold on. Well, I think it's not. It's not like, no, it's not. Never mind.
It's technically, it's definitely not. Because even though it goes like in sections, what do you see about those gradual sections? They keep going down, right?
That means it's not even balanced. Someone needs to be told that.
All right, so let's discuss. Is mechanical energy conserved in this graph that I'm showing you right here? No, it is not. Okay? So, Christine, just because I heard you talking about it, right? The pluses and the boxes, those are representing our individual types of energy, right? It doesn't say which one's which, but as the pluses go up, the boxes go down, right? And as the boxes go up, the pluses go down. And we said that kinetic energy and potential energy are pretty much mirror images of one another when energy is conserved. But this line up at the top, right, is that a straight line? It is not. This is actual data that took of, if I remember correctly, I think this is a ball that is flying through the air, up and back down, and I caught it again. Okay? So, kinetic energy, right, decreases and then increases, because as I throw the ball up in the air, the first thing that happens to the ball is, right, slows down, slows down, slows down, then it speeds back up. So the kinetic energy is going to go down and then come back up. But the potential energy, right, as the ball goes higher into the air, sorry, I should do this, right? There's my ball, right? Threw it up in the air, and then it came back down like this, right? Okay? Go.
Box missing at the bottom. I don't. Is that supposed to?
This one?
No, like at the very end.
Yeah, I think I cut it off just because.
Okay.
Zoe, at the end the graph gets a little bit crazy, so
Like,
it should have another box there, but at least from a general shape standpoint, right? Okay. So as this ball goes up, it comes back down, right? Right when it leaves my hand, okay. So if this is my here, I'll use orange. Okay. So if this represents my hand, ooh, my arm is real skinny, right? All right, so there's my hand, right? As soon as it leaves my hand, what is that ball doing? Is it moving or not moving? Definitely moving, right? So it's going to have some kinetic energy. But the ground is way down here. So is the ball at the ground when I let it go?
No.
No. So it still has some potential energy, even though it's still moving, right? So as the ball goes up, right, on this up trip here, what's happening to the kinetic energy? Andrew?
It's going down.
Because what's happening to that ball on its up trip?
It's gaining potential energy.
Why? No, let's talk about the kinetic energy. What's physically happening to the ball as it goes up into the air? It slows down, right? Okay? And if it slows down, that means that the kinetic energy is going to decrease. But as it's slowing down, which way is it going? It's going up, right? So its potential energy is increasing, right? But once it reaches the top, well, what has to happen to it up at the very, very top? It stops, just for an instant, but it does. Take a look here, right? What's the kinetic energy at that point? 0, right? And does potential energy get any higher than it is up there? That's the highest point, right? And then the opposite happens on the way down. Potential energy decreases as kinetic energy increases. Because on the way back down, what happens to that ball? Faster, faster, faster as the height gets lower. But the whole point of this being that if you looked at the total, right, it's not the same. It keeps getting lower and lower and lower. Meaning, was gravity the only thing acting on that ball as it flies through the air? No, because gravity is a conservative force. And conservative forces would keep the total amount the same, but it's not. Okay? Good there? What does that ball encounter as it flies through the air? Wind resistance, air resistance, anything that we want to call it. But that's not a conservative force. That's a non-conservative force. Okay? Same thing happens with this pendulum. Okay? So there's the pendulum. And it goes like this, and it goes like this, and it goes like this. But if you look over here on the side, there's a little slider bar that says friction. And right now it's set at how much friction? None, right? Is that the real world?
No.
It's not the real world. So let's increase the friction a little bit. Okay? So now I have increased the friction, and a new line starts showing up on my set of bar graphs, right? What line is starting to show up on that bar graphs? Thermal, right? This red line right here, keeps getting bigger and bigger and bigger. Because like we talked about on Monday, when friction acts on stuff, what happens to the mechanical energy?
It lowers.
It lowers because friction turns mechanical energy.
Negative force.
It does negative work, right? But what does it turn that mechanical energy into? Rub your hands together. It turns it into thermal energy, right? Okay. Jillian, at the beginning, you said that mechanical energy is conserved because this total energy bar stays the same height, right? Okay? In this example, even now that we have friction, that total energy bar is remaining the same height, right? But now we see that more and more and more of it is being taken up by what? By that thermal energy. So the total energy is conserved, but the different forms keep changing. Okay? Good there? All right. Short video. If you are watching on the recording, you probably won't see the video because it doesn't record streamed things. It just looks like a black box. Okay? But this is a short video that is called Nose Basher. Okay? It is a whopping 47 seconds long. So hopefully you'll be able to keep your attention for that long. All right? I'm going to turn this up. And it's going to make that buzzy noise. Hopefully you'll be able to hear it. So here we go.
Nose basher. When Bill raises the bowling ball to his nose and is about to let it go without pushing it, the total energy of the ball is all in the form of gravitational potential energy. But as the ball swings down to its low point at the bottom, that potential energy continuously decreases as the ball's kinetic energy increases. By the time the ball has swung back up to its high point near Bill's nose, it has lost all its kinetic energy, but gained back almost as much potential energy as it had when he first released it. This is why Bill is still smiling. We'll find out why the ball doesn't quite swing back to its starting point in our next demonstration.
Alright, so that is a classic physics demonstration. No, it won't hit him.
I wished it would hit him.
Oh, you wished it would hit him. Great. Okay. So that is a classic physics demonstration. I have done it on several occasions, but I don't have a bowling ball pendulum in this room. So you start off, you take this bowling ball, you hold it right up against your nose. You can touch your nose if you want to. And you let it go. And it goes across, and it comes straight back at your face. But it does not hit your nose. It will not hit your face. Okay? Because that entire time, that it has been swinging, right, is gravity the only force acting on it? It's got to contend with friction and air resistance and all those things. That being the case, will it ever get to the amount of gravitational potential energy that it started with? And if it doesn't have the amount of gravitational potential energy that it started with, will it ever get to as high as it started? No. On your outline, you have a picture, or 3 pictures, of this girl. Okay? So this girl does the same demonstration that the nose basher did, right? Here's a picture that shows the kinetic energy and the potential energy and the total amount of mechanical energy of this pendulum as it swings back and forth. Okay? Notice the blue dotted line, which for you guys is the one that kind of looks like a sine curve, right? It starts off high, goes low, because, right, the pendulum starts here, and as it goes down to the middle, it goes low again, right? But it goes back up, but does it ever reach the height that it started? It never reaches that height again, okay? Because there's should be 2 more lines on that graph. And those 2 lines look like this, and you have those 2 lines on the 3rd picture. What does the red dash dot dash dot dash dot line represent? That red dash dot dash dot line is going to represent thermal energy. Because the longer the pendulum goes back and forth, what's happening to that line? It's increasing. What's the green line represent up at the top? Total amount of energy. What could we say about the slant of this red dashed line and the slant of this red dash dot line? If mechanical energy is decreasing, what has to be happening to thermal energy? Increasing. How much? Same amount. So if we look at the slant of this line, how much should this line be slanting? Same amount, just which way? Opposite direction. Good there? We okay with that idea? All right. Let's put that away. Actually, keep it out. And let's take a look at this sheet that I gave to you last week. It's got these 3 cars up on the top of it. And we talked about how fast it was going and how much work was done and stuff like that. And then at the bottom of the front page, we talked about the ball on this ramp and these steps, and how high it was and how much energy it had, blah, blah, blah. Let's flip it over to the back side, and we are going to take a look at these 3 ramps right here. Okay? All right, so it says, figure to the left shows a 10-kilogram box being lifted to the top of a 5-meter tall ramp. The box is then slid down the frictionless ramp back to the ground. Use this information to answer the next 3 questions. So, first question. Calculate the PEG that the box has at the top of the ramp. Last week, we talked about calculating the amount of potential gravitational energy something has. And the amount of potential gravitational energy something has depends on 3 things. Right? What does it depend on? Pretty good.
Mass, height, and gravitational
Pull, right? Or acceleration, to be specific, right? So PEG equals m times g times h, right? Do we know m for this box? What does it tell us in the information of the problem? 10 kilogram box. That's m, right? Do we know g? Do we know the effective gravity here on Earth? 9.8, right? Okay. Do we know h? Yeah, they gave us h, right? They said that this is a 5-meter tall ramp, right? So now it's just a matter of plugging in those things we know, right? So PEG equals the mass of that object, which is 10 kilograms. I'm just going to conveniently leave out the units right now, okay? Then the effective gravity, the acceleration of gravity, 9.8, right? And then the height, which we said was 5 meters, okay? So you plug that all into your calculator. Actually, I should have added a few more things on here. This is actually 10.0, and this is actually 5.0, okay? So you run that into your calculator, and what do you end up with? Trey?
490.5. Well, I did 9.81.
Okay, so let's go 490, right?
Okay.
Okay, so 490, okay? First, as far as rounding goes, okay? 2 significant digits, two certain, 1 uncertain. 1 certain, 1 uncertain. 1 certain, 1 uncertain, right? So, this answer, certain, uncertain, this one doesn't count, okay? That one is just being a placeholder, okay? So 490 is what we're going to keep it as. Unit, what unit goes on it?
Joules.
Because we're measuring energy, that unit's going to be joules. Okay? Good, Catherine, go ahead.
Because, like, with the gravitational,
Yep.
isn't it one certain and one uncertain?
Yes.
And we always go with the least?
Right.
So why is it 2 certain and 1 uncertain?
Now, in this case here, okay, Catherine, we're going to learn these rules a little bit more, we're going to learn these rules in more detail in a couple weeks, okay? This 0 doesn't count in this case, okay, because there's no decimal point there. If there was a decimal point there, that makes the 0 count, but because there isn't, it doesn't count, okay? Catherine, oh, too far. Catherine, I'm not going to hold you responsible for the rounding on like the quiz or the test, okay? I'm introducing you to these ideas. I will formally introduce you to them later on when we talk a little bit more about significant digits.
So
Okay.
if I had written 500, you would.
I would be okay with that, right? Now, it's probably a good idea. Did you get 490 when you put it in your calculator?
Yeah.
And then, so it might be a good idea for you to write it and then draw me an arrow to show me 500 like this, to show me that's how you rounded it. That's not really what you got, but you rounded it that way. Like I said, I'm not going to hold you responsible for that, but it's a good idea just so I know, okay, that's just a rounding thing. She really knows what she should have done. Okay, not good? Okay. All right. Question number 2. What is the speed of the box at the bottom of the ramp in case number 2? Okay. There was an important piece of information that they told us about this ramp in the information of the problem. And what did they tell us about this ramp, Omar? It's frictionless, right? It is a frictionless ramp. Meaning, Omar, what is the only force that's pulling that box down the ramp? Gravity. And what do we know about gravity? That's how much it costs. That's acceleration. What kind of a force is gravity, Omar? Do you remember? I don't want to know if Trey knows. I want to know if you know. Well, I'm asking you. I want to find out if you know or not.
No.
Okay. So, what kind of a force is gravity? Conservative. All right. Hey, this is how I find out what you know and what you don't know. Okay. All right. So gravity is a conservative force. Okay. And we said that if conservative forces are acting on an object, the total amount of mechanical energy at the beginning has to equal the total amount of mechanical energy at the end. And what do we call that idea? Conservation of mechanical energy. So in this case, because the ramp told us the ramp is frictionless, mechanical energy will be conserved. Now, mechanical energy is made up of a bunch of different things, right? So, up at the top of this ramp, before the box slides down, right, it's up here, sitting up at the top, okay? What kind of mechanical energy will it have up at the top of the ramp? Okay. Christine, go ahead. Okay, so it definitely has potential energy, right? So we know that there's a little potential energy at the beginning, PEG, okay? Is it moving when it's sitting up at the top of the ramp? No. So that means it doesn't have what? Doesn't have any kinetic, okay? Was anything stretched out or scrunched together or anything like that? No. So it doesn't have any elastic potential energy? No. So the only thing it has at the beginning is gravitational potential energy. So now we've talked about the idea that as it slides down the ramp, what starts happening to the potential energy? It decreases, but as it's decreasing, kinetic is increasing. Where does this box eventually end up? On the ground. So how much potential energy will it have at the end? 0, right? Because we said potential energy depends on height. If it's at the ground, it's got 0, okay? But what is it doing now when it hits the ground? What is it doing at the bottom of this ramp now?
Nothing.
Say again?
Nothing.
What has it been doing the whole time it's been sliding down that ramp? Speeding up, speeding up, speeding up, speeding up, right? Remember, this ramp is frictionless. So right when it gets to the bottom of the ramp, right, what's it going to be doing? Not on the ramp it's not. When it gets to the ground maybe, but right at the bottom of the ramp, what's it doing? It's going fast, right? Because it's been going faster the whole time, the whole time, the whole time. There's no friction on that ramp. So it just keeps going faster and faster and faster, meaning that it's gaining what the whole time? It's gaining speed, but it's also gaining kinetic energy, right? Down at the bottom of this ramp, it is now going to have kinetic energy, okay? We've already established that if it ends up at the ground level, it won't have any potential, right? Anything stretched out or scrunched together during the course of this box running down the ramp? No. So we don't have to worry about elastic energy. So we know from an energy standpoint, it starts with potential gravitational energy and ends up with kinetic energy. How much? What did we say about these graphs that we drew before?
Total mechanical energy total remains the same.
The total remains the same, right? But Zoe, what about the red and the yellow? What happens to red? What happens to yellow?
As gravitational potential energy decreases, kinetic increases, or vice versa.
As one goes up, the other one goes down. How much?
The same.
The same amount. So, do we know how much potential energy this box started with up at the top? Right? If we do, then we also know how much kinetic energy it ends up with at the bottom. Right? So now we can say that at the bottom of this ramp, the kinetic energy equals 490 joules. Does that make sense? Does it make sense to everybody else besides Trey?
Yes.
All right. But that's not what this question asked us for, right? What does this question ask us for? Speed, right? So, I gave you a formula for kinetic energy last week, right? What's the formula for kinetic energy? 1/2 mv squared, right? So I'm going to substitute that formula into this equation where it says Ke. But the other side of this equation is still going to be equal to what? 490. Right? So now, we want to solve for what in this formula? V, right? We want to solve for V. Do we know what M is? We know what M is, right? Okay, so I'm going to take this and just put it on a separate page, okay? Because I know that some of you whiz through the math and some of you don't, okay? So, it told us before that the mass was 10 kilograms. So I'm going to plug 10 kilograms in here. V is still unknown, and that together, that all has to equal 490. Okay? So there's a couple things you could do to get V by itself. Okay? I don't necessarily care how you do it, as long as you end up with V by itself. So, what's first thing we could do here? Catherine, what would you do first?
Well, this is just,
Okay, go ahead.
if the kinetic energy and the potential and the gravitational potential energy are the same.
Yep.
Then why couldn't we just say that the gravitational potential energy is 490?
We did. Right?
But then they would be the same, so.
So that means this equation is good, right? Because 490 equals 490, right?
Okay.
Okay? So that's kind of the jump that we made to get that, to know that the kinetic energy is 490, right? But now we don't want to know what the kinetic energy is, right? Does that make sense?
Yeah.
Okay? All right, so mathematically, what's the first thing we can do here? Like I said, there's lots of ways you can solve this. Christine, what would you do first?
I would divide 5 by 2, so it would be 5.
Okay, so you would multiply 1/2 and 10 together, right? So that means we'd end up here with 5 times V squared equals 490. Okay? What next? Go ahead, Christine.
Divide both sides by 5.
Divide both sides by 5, so that would give us V squared equals whatever 490 divided by 5 is. What is it?
98.
98. Okay? Last step, what would we do now? Take the square root, right? Because we don't want V squared, we want V, right? So then we take the square root of this, you should end up with something a little less than 10.
Yeah.
9.8. Yeah. So, okay.
9.89.
Is it 9.89? Is that what you got?
We need
So then we probably go 9.9 then with our rounding, right? All right, good there? Good with that? If it's not, I won't go, the rounding one on this one is a little bit more complex, okay? So let's not worry about the rounding. Did you get 9.89?
Yeah.
Then that's fine. You're good for where I want you to be right now, okay? All right, are we okay with this? Okay. That's the answer to question number 2. Question number 3, we don't have to do any calculations to answer. It says, will the speed of the box be any different at the bottom of the ramp in case 3? So, in this case, right, the box starts from up here and it slides down the ramp, but the ramp is different. Will that affect how fast that box is going at the bottom? Good. No, because it's frictionless. Okay? If we look at it from an energy standpoint. Oh, not that one. It's going to look weird. Okay? If we look at it from an energy standpoint, on this ramp, ramp 3, what kind of energy will it have up at the top? Still has what kind of energy up at the top? potential, right? And then at the bottom, what's it going to have? Kinetic. Potential energy depends on height. Does it start at any different height in 3 than it does in 2? So it's still going to have this much potential energy up at the top. And if the ramp is frictionless, how much kinetic energy is it going to end up with at the bottom? Same amount, regardless of the fact that the ramp is turned. If it's frictionless, that doesn't matter. Same height, same speed at the bottom. Good there? All right. Let's get off of this and move on to the next parts. Okay? Today. Oh, before I do that, sorry. Last night, there was some homework on the calendar that was off of the sheet that I handed out at the beginning of class that says conservation of mechanical energy, conservative forces. Did you guys get that sheet? This one? It looks like this. It's got the picture of the roller coaster on it. Thanks, Rachel. So, first off, this sheet that has the roller coaster on it, okay? If you didn't get a copy of it, it's back on the tray in the back, okay? The bottom part that says work energy theorem down there underneath the roller coaster, cross it off. We're just going to disregard that whole part, okay? I did some analysis of last night, and I figured you guys weren't ready for that yet, so we're going to just get rid of that, okay? But up at the top part says conservation of mechanical energy. Those problems are very similar to the problem that we just did in class, okay? So last night on the calendar, okay, first, this part here that says work energy theorem number 2 and 4, you don't have to do that. But for tonight, if you would try number 2, number 4, and number 5, like I said, they're very similar to the problem that the example that we just did. Give you some practice doing it. Okay? Good there? Okay. Lab. Last week you started gathering data for this lab about the pendulum as it swings through. I believe that several of you did not get that data completed. Okay? Today, finish up that data collection. Then there is a part 2 to this lab where you're going to gather a similar kind of data, but now for a ball rolling down a hill as opposed to a pendulum. Okay? Ball rolling down a hill. See those wooden boards back there on the ledge? Those are your ramps. There is a plastic container that has golf balls right next to it. That's your object rolling down the hill. You can use our old books to make your ramp. Okay? So that's your setup for the second part. My suggestion to you is to collect the data for the first part and the second part before you start doing calculations. Save the calculations for when you have all the data collected, because you can do those anytime. You need the data collected here, though. Okay? LabQuest photo gates are in the back cabinet. Balances, you're going to need the balance because you need to mass the golf ball. There's one out, but I'll get a couple more out. Okay? Pendulums, some of the stands are still set up. If you need a stand, there's more back in the corner over there. Strings are back in the drawer. Pendulum bobs and stuff are on the window over there. Meter sticks are on the window ledge. Go.